Hello viewers, I am Dr. G. Littlefla, faculty from the Department of Physics, Stella College, Vijayawada. Welcome you all to another interesting topic called BCS theory of superconductors. In one of our video, we have discussed about superconductors and their principles and their applications. Now today we will discuss BCS theory of superconductors. BCS theory, each letter represents the name of the scientist. John Berdin, Leon Neil Cooper, John Robert Schiffer. These three scientists shared the Nobel Prize in the year 1972 for physics for their contribution towards superconductivity, and they named it as BCS theory. Objective of today's talk is students will be able to learn about BCS theory of superconductivity. The outcomes will definitely be that you will be able to explain why materials lose their resistivity when they are cooled below the critical temperatures or when they become superconductors. You will be able to describe lattice distortions due to flow of electrons in superconductors, discuss electron-lattice electron interaction via phonon field, and you will be able to outline the influence of formation of Cooper pairs in superconductors. We know metal is a crystal. So a crystal structure means arrangement of atoms. These red dots are called atoms or ions or molecules. So in metal is a solid. So metal is a solid crystal structure in which the atoms or ions or molecules will be regularly arranged, and that arrangement will be repeated in all three dimensions like this along x, y and z axis. So there is a regular arrangement of atoms or ions or molecules, and that arrangement is repeated in all three dimensions. This is what called crystal lattice. So this location of each atom or ion, this is called lattice point. So we have lattice point. So like this, the crystal structure will be formed. You would have studied in one of your physics course that the structure could be simple cubic lattice structure, simple cubic crystal structure, body centered cubic structure, or face centered cubic structure, etc. So here what I want to try to say is these atoms are arranged in a regular pattern. Normally at room temperature, some of the electrons would have left the atoms, so making the atoms to become ions, and these ions will not be at rest. Atoms or ions or molecules can be at rest only at absolute temperature. Any temperature above absolute temperature, they will be in a state of vibration, definitely sending out some energy. Okay, so what happens when electrons leave? Some of the electrons have left. Simply I have marked few only. So these atoms become ions. Now these electrons are called free electrons, and they move freely anywhere in the crystal structure, in the crystal lattice. So when these free electrons move across the crystal structure, there could be a collision between the electrons and the lattice points or the ions in the crystal, because you know ion, by losing an electron, it becomes positively charged. Electron has a negative charge. So this ion and this electron will attract each other. As a result, you can say when the electron goes near the ion, a collision has taken place. So due to this, so the electrons cannot freely move across the crystal. So they are constantly attracted by the ions in the crystal. As a result, they experience some resistance to flow across the crystal. We know current. How will we define current? It is a flow of electrical charges. Okay. So in conductors, when the current flows, the material offers less resistance, so the electrons can be conducted from one end to the other end freely. Whereas in insulators, these electrons experience lot of resistance, so they will not be able to move freely. That's why that crystal behaves like an insulator. So the electrical resistance arises because of the collision of conduction electrons with the vibrating positive ions in the crystal. This results an increase in resistance of the material. Also, due to collision, some heating also will be developed. So when current is passing through the wire, if you touch and see, not the insulating part, that metal part, if you touch and see, slightly it will be heated up. This heat is coming due to the collision between the free electron and the vibrating positive ions in the crystal. According to BCS theory, when current flows through a superconductor, an electron experiences an attractive force when it passes near the positive ion in the lattice of the superconductor. Now, due to this attraction between electron and the ion core is slightly displaced towards the electron. So, this picture depicts this nature. See, it's that metal is a crystal structures. Means the ions are regularly arranged very nicely. But now, when there is a free electron, some distortion is taking place here. What happens? These ions, by losing electron, they have become positive. And these ions love to attract back the electron and convert itself into an atom. So, when a free electron is moving across a crystal, these ions try to attract the electron to themselves. So, as a result, they just bend away from the regular pattern. So, these ions have displaced from their regular position. So, the crystal structure is getting defected. So, you can call that there is a distortion taking place here. So, this kind of distortion leads to an increased positive charge in that area of distortion. So, here this is the area of distortion. You can see many positive charges are here. This is known as lattice distortion. That means the ions which are regularly arranged in the lattice get displaced from their locations and move towards the electron. So, from the second lattice plane, these ions have moved towards the electron. So, this is what called distortion, lattice distortion. Some defect has taken place at the crystal lattice due to the presence of this electron. The distortion in the lattice then travels away as a mechanical wave called phonons. What are called phonons? In competitive exam, they ask what is the difference between photon and phonon. Photon is quanta of light energy. Phonon means quanta of energy released whenever some distortion takes place in the crystal lattice. So, phonon is a quanta of energy released whenever some distortion is taking place. Now, suppose the crystal lattice is distorted, some positive ions have moved towards the electron. Now, before these positive ions go back to their original position, if another electron is entering, now what happens? Let us see. Now, suppose that another electron comes near the distorted lattice before the crystal lattice bounces back to its normal position. Now, the lattice vibration, that means phonon, interacts with the second electron, and hence there is a force of attraction between the second electron and phonon. So, it may be appearing Greek and Latin to you, but in the simple term, these three scientists have explained very beautifully. Now, let us say that from the crystal lattice, we have chosen only two ions. Now, we consider one electron. Electron has particle nature as well as wave nature. Its wave nature is represented by the vector called K. So, let me say the electron, free electron with the wave vector K is approaching the crystal lattice. Now, this positive ion is coming towards the electron, so causing some distortion. Now, what happens? The incoming electron shares some of its quanta of energy with the ion and it moves out as K minus Q. The quanta of energy what is shaded here is Q, represented by Q. Okay. Yeah. Now what happens? Some distortion has taken place. That electron, while moving closer to the ion in the crystal lattice, some distortion has taken place. So the electron is changing its direction. So it is going away like this with the wave vector K minus Q. That means this minus Q, that means this quanta of energy is given out in the crystal due to this lattice distortion. So this energy, quanta of energy, will travel in the form of a wave in the crystal lattice. Now before this ion go back to its initial position, let us assume that there is one more electron whose wave vector K1 is coming. So when it is coming, before it is going near to this ion in the lattice, it absorbs some excess energy here, some phonon energy here. So what happens? This electron, instead of interacting with the second ion, absorbs this phonon energy and moves away from the crystal with the wave vector K1 plus Q. So we have taken two positive ions of the crystal lattice. We consider two electrons. The first electron, when it is coming near the positive ion, it loses some energy and moves with the wave vector called K minus Q. And this lost energy is given out in the form of a wave, and it is traveling across the crystal lattice. So before this ion goes back from the distorted state, another electron is coming with wave vector K1. This wave vector K1 has to react with the second ion, but instead of interacting with the second ion, it absorbs this phonon of energy and moves away with a wave vector called K1 plus Q. In this way, two electrons interact with each other through the lattice vibration. So what is called lattice vibration? The ions will be vibrating in the lattice, crystal lattice. Okay, so they will be vibrating naturally. When electron comes, the positive ion tend to distort the crystal lattice, tend to move towards the electron. As a result, the crystal lattice gets its momentum gets accelerated. So this electron is losing some energy. So its wave vector becomes K minus Q. This energy, quanta of energy, is traveling in the form of wave, and the second electron absorbs this quanta of energy and moves away from the crystal lattice with the wave vector K1 plus Q. So you call that these two electrons with wave vectors K and K1 have interacted with each other due to this lattice vibration. Okay, so this process is called electron lattice electron interaction via a phonon field. What is phonon? Quanta of energy that is being released due to the interaction between the positive ion in the crystal lattice and the free electron. So electron lattice electron interaction via phonon field is shown in the figure. When an electron, all this I said. So a phonon of wave vector Q is emitted. Why? Due to the distortion in the crystal lattice. This positive ion is bending towards the electron. So due to this distortion, a phonon of wave vector Q is emitted. Right? All this I explained. Now what happens? You just see before the lattice interaction, the two electrons had wave vectors K and wave vectors K1. After the interaction, the wave vector of the first electron becomes K minus Q and the second electron becomes K1 plus Q. So these two electrons have opposite nature, so they attract each other and form a pair called Cooper pair. The electron with the momentum K minus Q and the electron with the momentum K1 plus Q forms a pair of electrons. and it is called Cooper pair. We know electrons will repel each other, but here, due to the change in its momentum, variation in the momentum, they attract each other and form a Cooper pair. One of the scientists' name is mentioned here, given to this pair. Therefore, Cooper pair is bound pair of electrons formed by the interaction between the electrons in the phonon field. What is called phonon field? This way. In the crystal lattice, when a quanta of energy begins to travel in the crystal lattice is called phonon field. This phonon field is coming due to the distortion taking place in the crystal. So the Cooper pair is a bound pair of electrons formed by the interaction between the electrons in the phonon field. Now the two electrons which paired up have opposite momenta and opposite spin. So we know electron will be rotating about itself. So the two electrons, you can see the electron is moving this way and this is this way. So their spins are different, they have opposite momenta, and such electrons forms a pair, and that pair is called Cooper pair. Now these paired electrons, although they are two individual electrons, they form a pair, and now onwards, after forming the pair, now onwards they begin to move across the crystal as a single unit, and they cooperate in their passage through the superconducting material crystal structure. For example, when these electrons are formed as a pair, that cannot be attracted by the positive ion in the crystal lattice, because you see this positive ion will attract the electron naturally, but another electron, these two electrons are in the bound state now. So one is having opposite momenta, another is having positive momenta. So the crystal ion cannot attract them. So there cannot be any distortion. Because these two electrons are they having their spins opposite, having their momenta opposite. So the positive ions are not able to attract these electrons. So what happens? Suppose if this positive ion is trying to attract this electron with the momenta k minus q. Now this electron will not elevate, it will not break up the pair. So it will try to attract k minus q, electron with the k minus 2 q wave vector. So this ion will not be able to break the pair, and so it will not attract the electrons, because the electrons are now in phase and ions, their influence will be lost here. So as a result, these two electrons with the momenta k minus q and k1 plus q with opposite spins forms a pair and nicely sail through the crystal. Yeah, it is this process that links two electrons that normally should repel each other. Electron having negative charge, another electron having negative charge, generally will repel each other. But what happens? With the help of their momenta, with the help of their opposite spins, they are entirely opposite to each other. Opposite entities will attract each other, so they form a pair. The forces exerted by the phonons or the vibration in the crystal lattice overcome the electron's repulsion. Normally, electrons should repel each other, but because of the presence of phonons or the positive ions vibrating in the lattice, make them to attract each other. So now the electron has with one clockwise spin and momenta k minus q is forming a pair, a bound system with another electron with opposite spin and having the wave vector k plus q. Now they form a pair. Now as a pair, they begin to travel across the crystal in the forward direction, because this ion, this is a bound pair. This crystal ion or this or any crystal ions, if they try to attract this electron will pull back this electron towards it. So these ions in the crystal will not have any influence over the Cooper pair. So if this ion is pulling this electron, maybe this electron will not elevate. Suppose if this ion is pulling this electron will not elevate. So as a result, they form a pair As a pair, they move across the crystal. Okay, the Cooper pair of electrons moves on without suffering any deviation or scattering or collision with the impurities or thermal vibrations. Due to thermal vibrations, they don't. Even normal temperature cannot break the Cooper pair. So they don't collide with the lattice ions. The crystal lattice ions, they sail through very smoothly without colliding. So their speed will not be reduced, they cannot be scattered, all that will not take. There is no distortion at all. Simply the crystal structure is preserved, all the ions will be regularly arranged. These ions cannot bend towards this electron and cause distortion, because these two electrons are having opposite nature. So if it comes near this electron, and this electron with opposite nature will repel the crystal ion here. So as a result, all the crystal ions continue to be in the regular pattern, and these Cooper pairs will smoothly sail across. So there is no exchange of energy between pair of electrons and the lattice ions. That means there is no collision between the pair of electrons and the lattice ions. As a result, when there is no collision, there is no heat energy generated, or there is no resistance at all. If an electric field is supposed to this crystal structure, if we connect an electric field, what happens? These Cooper pair from one end to the other end, they just travel forward, contributing to the current. So if an electric field is established inside the substance, the electrons gain additional kinetic energy and give rise to a current. Otherwise, they will be randomly moving. Now it's a directional movement, it will give rise to the current. The main important point is that the pair of electrons does not transfer any energy to the lattice and do not get slowed down. So once the Cooper pair is formed, if this ion bends and cause towards this electron and cause some distortion, this electron will oppose it. Suppose if this lattice ion tried to attract this electron, the presence of the electron with opposite nature will not allow this to happen. So there is no distortion taking place in the crystal lattice, and without any resistance. Means if they collide with the lattice ions only, their speed is reduced, and this property only we call it as resistance. What is resistance? The property of the material that opposes the flow of charged particles, that electrons. So here there is no opposition, there is no collision, so smoothly they flow through the crystal. As a consequence of this, the substance does not possess any electrical resistivity and conduction is large. So if current is given to the superconducting material, that current will last in that material for a longer period of time. So this is what this electrons, when they form Cooper pair, they do not encounter any collision or scattering with the lattice ions, and so the resistance disappears and conductivity becomes infinity, and the substance becomes a superconductor. As long as the superconductor is maintained below its critical temperature, the Cooper pairs are able to stay together due to the reduced kinetic molecular motion of ions in the lattice. There is no distortion in the crystal lattice. So as long as the material behaves like a superconductor, these electrons which are paired continue to be in the bound system, and their movement will be very free. They do not experience any collision. So Cooper pairs gets broken as the temperature of the material rises. We know when it is behaving like a superconductor, it's okay. Suppose if the temperature of the superconductor is increased, what happens? The material loses its superconducting nature and becomes ordinary conductor. Ordinary conductor means naturally what happens? The Cooper pair, so superconductor becoming a conductor means the Cooper pairs will be broken and the electrons will be independent, and now what happens? The distortion in the crystal takes place. The crystal ions will attract the electrons, or the electron will have collisions or scattering with from the crystal ions, as a result, their speed gets reduced. So you can say the material has developed some kind of resistance. So when there is resistance, the material becomes an ordinary conductor. When it is cooled below its critical temperature, it behaves like a superconductor. In the superconducting state only, the electrons can pair up together and oppose the collisions with the crystal ions. That way, in superconducting state, the material loses its total resistance and it behaves like a superconductor and becomes a very good conductor of electricity. I hope you have understood this simple concept, but this idea was not there. Now, after understanding, we feel that it is very simple. Forming electron pairs. This could happen only in the superconducting state. If you increase the temperature of the superconductor, that temperature provides some energy to break the Cooper pair and the electrons cannot be paired at all. So easily while moving, electrons are very light compared to the weight of the ions, crystal ions. So easily when they move, they get collided with the crystal ions and their speed gets reduced, they pick up resistance and they become normal conductors. So BCS theory, for this, these three scientists simply telling that electrons exist in pairs, not as an individual entities. Electrons in superconducting state exist in pairs and reduces the distortion. For this fact, these three scientists got Nobel Prize in the year 1972. I hope you have enjoyed this talk. This BCS theory of superconductivity is an important concept, generally would be asked as an essay question. So students, if you please go through this 1 or 2 times, you will be able to understand the concept well and answer well. Okay, thank you all for watching this, for listening to me. Thank you so much.